Hey everybody, it's Mrs. Harbin. We're going to be looking for periodic trends today, so stick with me. 4 objectives. Read them, love them, learn them. This is a special request song by my son Dominic. Right? Make sure to read Chapter 6, Section 6.3. There will be questions. Alright, so I want you to remember all this. Another good reason for this song. Atomic size is also known as atomic radius. So if you look at an atom and you measure the distance from the center of the atom to the outermost electrons, you get the radius of the atom. That's the atomic size. But if you can't measure the distance of an atom's nucleus to its outermost electrons, well, if you know the distance between 2 nuclei in a diatomic element, half of that is the radius. Okay, so what is atomic size? It's the radius, the distance from the nucleus to the outermost electrons. So another way to say radius is atomic size. Atoms get smaller going across. So this is a model of what the trend is. Look at these atoms getting smaller going across the periodic table. Why? Because more protons means stronger nucleus, means pull those electrons in closer. Pull electrons in closer. Okay. All right, so you can see atoms get bigger going across. What happens to atoms going down the periodic table? Well, they get bigger. I'm sorry, I said they get bigger going across. It's obviously smaller. Okay. Atoms get bigger going down. Okay, let's talk about why. Because electrons are going in higher energy levels. Where are higher energy levels? Further from the nucleus. Okay. So energy levels. Okay, so they're farther from the nucleus. If you memorize this periodic trend and group trend, you can explain all the other trends in the periodic table that we're going to talk about. Okay, so please take a mental picture of this right now. Look at it, click it, or tick it. So look at atoms get bigger, their atomic radius gets bigger going down, and they get smaller going across. Okay. Here is just a picture of the representative elements, which are groups 1 through 8, and they represent the trends in the periodic table. You can see all the properties of elements using just the representative elements. So they represent groups 1A to 7A, or 8A represent. Now the book says 7A, but I like to think that the noble gases also represent. Okay, look at it. Bigger going down, smaller going across. All right, so here is a vocabulary. Electronegativity. Oh my gosh, can I say it? Electronegativity. What is the definition? Write this down. Electronegativity is the ability to attract electrons in a bond. So the only time you can measure electronegativity is if elements form a bond. So here's the trend. F or fluorine is a what's up of the periodic table for electronegativity. Francium is not. So let's see where they are in the periodic table. Backing up to francium is down here. Fluorine is up here. They are pretty much opposites. So let's talk about why fluorine has a very great ability to attract electrons where francium does not. Fluorine is small and it's attractive because it has so many protons for its row on the periodic table. So it's going to be easy, it's going to be more able to attract bonded electrons easily because it's got a pretty strong nucleus for its size. All right, so I redefined the trend based on the size of the atom. And I said size and more protons attract. Okay, so electronegativity, here's the definition: ability to attract electrons when forming a bond. Fluorine is a what's up and francium is not. Okay, why? Smaller atoms have a greater ability to attract electrons in forming a bond. Okay, ionization energy, another property. Here's the definition. Ionization energy is the amount of energy needed to remove an outer electron from an atom. Okay. So, energy needed to make an ion by removing an electron. Ionization energy. Here's sodium atom, here's sodium ion. The energy it took to get that one electron out of there is ionization energy. Okay, what is the group trend? Group trend is up and down. Right? ionization energy decreases down a family. So it gets easier, takes less energy to take an electron from a bigger atom. Why? Okay. It's easier to remove electrons from larger atoms since the outer electrons are farther from the nucleus and shielded from the pull of the nucleus by core electrons. Whoa, I just threw some extra terms at you. Core electrons are not valence. Outer electrons are valence. What do we call all the other electrons? Core electrons. Okay. So bigger atoms have more core electrons and their valence electrons are farther away. So it actually is easier, another train going by, to take electrons from bigger atoms. So less ionization energy because it's easier. Right? Is there more to it? Well, there's a trend for a period on the periodic table. I wonder if you could predict it. We already know the size of atoms going across, they get smaller. So what do you think the ionization energy does? It increases across the period. Okay. Why? The atoms are getting smaller going across, right? So if you try to take the outer electrons from this atom, it's going to take a lot more energy than trying to take the outer electrons from that atom. Okay. So as the radius gets smaller, elements are more able to hold on to their electrons because of the more protons in the nucleus. So it takes more energy to remove an electron from a smaller atom. Okay. So valence electrons are in the outermost shell, and they're relatively easy to remove compared to core electrons. So this ionization energy trend is really for valence electrons. Okay. Successive ionization energy, so one electron after another electron after another electron. So here's magnesium. You try to take one electron from magnesium, it takes 738 kilojoules of energy. But if you try to take a second electron from magnesium, it about doubles, 1,450 kilojoules of energy. But if you try to take a third electron from magnesium, holy guacamole, the ionization energy dumps about what? Almost 4 times, okay? So why is it these two electrons are kind of easy to remove, but this one is not? Because these two are valence electrons for magnesium. This third electron is a core electron. We'll keep talking about it, but at least you have an example of that. So, explaining the main way atoms differ, and you just explained every trend. What's the main way atoms differ? In their size, their atomic size. So, let's talk about atomic size. Bigger atoms are less attractive because the outer electrons are so far away from the nucleus. So that means they have low ionization energy and low electronegativity. Okay? Nuclear attraction. More protons means more attraction, so that means smaller atoms. So the two things that help determine all the trends are the size and the nuclear attraction of atoms. So, ionic radius. What? Ionic means ion, radius means size of atoms. So this is the size of an ion. Right? So radius, we said atomic radius, ionic radius is the size of an ion instead of the size of an atom. Cations get smaller. Smaller than what? Smaller than their atoms. Let's talk about why. It's kind of like this onion analogy here. Oh, don't cry. Okay. So if you have an atom, but then that atom loses its outer electron, what's going to happen to it? It's going to get smaller. What happens to cations? They lost outer electrons. Okay, so cations are smaller than the original ion atoms. Okay, cations get smaller by losing their outer electrons. Anions get bigger. Oh, I forgot to warn you about the snakes. Anyway, snakes. Okay, so this is an anion. It's neutral, right? Anions gain electrons. What happens when you gain something? Look what happens to this snake. It gained another head. It got bigger. What happened to that snake? It gained 2 more heads and it got even bigger. So, gaining electrons means the ion is bigger than the atom. All right. Valence electrons are outermost electrons. Everybody in group 1A has 1 valence electrons. 2A, 2 valence electrons. Skip a few, 3 valence electrons in group 3A. 4 valence electrons. I feel like I've written this before. Hopefully you have and you're starting to get to know this. 6 valence electrons, group 6A. 7 valence electrons, group 7A. 8 valence electrons, group 8A, except for helium. Okay. It's also periodic. Look, go across this way, 1 through 8. 1 through 8. 1 through 8. 1 through 8. That's how many valence electrons they have. It's a periodic trend. So, why do elements form bonds? Why do elements react? The octet rule helps us know that. Octet, hopefully you hear the number 8 right there. Elements tend to gain, lose, or share electrons to become stable. So it usually results in 8 outer electrons. Some exceptions apply. So, like a disclaimer. But anyway, 8 is great. And so it helps us decide how many, what an atom's going to do to become stable. Aluminum. Aluminum is in group 3A. So how many valence electrons does it have? 3 valence electrons. So what is it going to do? Well, if 8 is great, any atom that has 3 or less valence electrons is going to lose them. They're losers. Aluminum is a metal. It's shiny. It loses its 3 outer electrons and becomes a +3 charged ion. Why? Well, once it loses its outer 3 electrons, then its inner shell or its core is filled and it's stable. Filled and stable. Okay. Once it loses those 3 outer electrons, so it's going to lose 3 electrons. All right, oxygen, it has 6 valence electrons. How do I know? It's in group 6A. So 8 is great. What's oxygen going to do? Well, it already has 6 valence electrons. The easiest thing, or the most common thing for oxygen to do, is to gain 2 more. Why 2? 2 more electrons. Why? Because 2 and 6 is 8. 8 is great. So when oxygen gains 2 valence electrons, it now is 8, and then it's going to have a full shell. Okay, metals and nonmetals react differently. Metals lose their electrons to become positive because metals will have 3 or less valence electrons. Nonmetals gain electrons to become negative when we're talking about ions. Nonmetals can also share, but nonmetals gain to become negative ions. So metals lose, but they're big losers, but don't worry, it's a positive thing to make it. Nonmetals gain and they gain ions. All right, so what are going to be the best reactors? Well, it depends if you're a metal or a nonmetal. The best metal reactor is francium. Find it on the PT, francium. Okay. Why? Because it's a big, unattractive loser. By big, I mean it's a big atom. It's at the bottom of its row. Okay, francium is way down there. Unattractive because it's a big one of the big atoms for its row, then it can't attract electrons to itself. So loser, it's going to lose its outer electrons pretty easy. Big because electrons are far away from the nucleus. Electrons far from nucleus. Okay? And it's unattractive because hard to hold electrons when they're so far away. And so far away. So it's going to react pretty readily. It's going to lose those electrons pretty quick, pretty fast. Reactive. Okay. The best non-metal reactor is going to be the total opposite. So fluorine. Oops, dropped it. Fluorine. So what is fluorine? It's a small attractive stealer. Small because if you go across this way, atoms get smaller going across. Okay, so here's fluorine. All right. And it's going to steal electrons because it's got a strong nucleus and a small size. Small size because proton attraction for valence electrons. Attractive because it's small and strong nucleus. Okay, so moving on. Most reactive elements on the periodic table. Well, it depends. Are we talking about metals or non-metals? Woo! Metal winner is the big, unattractive loser, francium. Non-metal winner is the small, attractive stealer, fluorine. Okay. What about these guys? No reactions. Why? Well, if we count their valence electrons, 5, 6, 7, 8, except for helium. They all have 8 valence electrons. What do we say about 8? 8 is great, so 8 is stable. Okay, 8 is great, 8 is stable. All right, so we're almost done here. We're going to play some music while we review. Okay. There are group trends, up and down trends, and periodic trends. Group, periodic, group, period. Okay. Knowing atomic size can explain everything. Metals are losers, but it's a positive thing. Quiz yourself. Quiz me. Quiz your lunch table. All right. Read chapter 6. I told you there'd be questions. All right. If you look on page 177, there's a checkpoint. Page 177. Okay. You have to know the definition of electronegativity to do it. Please answer question number 23, page 178. Okay. Hey, It's the bullet points again, the objectives. All right. Hopefully you remember these for centuries. All right. On the periodic table, you find valence electrons, protons, chemical properties, ion formation. Can you describe atomic radius, ionic size, electronegativity, ionization, and reactivity? Hope so. What about that octet rule? 8 is great. Okay. Full orbital stability. We will practice this one in class. Peace out.